All right, in this video, we're going to be talking about pure substances and mixtures. And as you go through these videos, if I'm going too fast for you, feel free to pause the video, slow things down, take your time. If you have a question that you want to be answered, feel free to reach out to me. I'd be happy to respond and clear up anything that maybe I was unclear about in one of these videos. So please let me know. So again, we're going to be talking about pure substances and mixtures. And once I get control of my laptop back, there we go. Here's our goals. We want to be able to distinguish between pure substances and mixtures at both the macroscopic level and the particulate level. And we also want to be able to distinguish between homogeneous and heterogeneous matter. So here's an example. So this plot over here on the left shows water and a solution of salt water. Okay, so data for each of those substances. So this is plotting their temperature as a function of time, okay? And at normal pressure, pure water boils at 100 degrees Celsius, right? So the temperature will remain constant until all the water has evaporated for pure water. So if we start here, the temperature increases, okay, increasing, stop, the water's boiling, and it remains constant until all the water has boiled away for pure water. Okay, for the salt water solution though, it boils at a higher temperature, okay, and the temperature will also increase as the boiling proceeds, right? So this is different in pure water. Temperature is going up and up and up and up and up as the water is boiling, okay? So why is this example important? Well, there should be an animation there. Interesting. Well, I'll just say what's supposed to be there. It highlights the differences between pure substances and mixtures. Okay, these two things, pure water and salt water, are behaving differently. They have different properties. And that's why we want to investigate the differences between pure water and salt water, or pure substances and mixtures is actually what I meant to say. So, by definition, a pure substance is a single chemical, one kind of matter entirely made up of one type of particle, which is maybe a few different ways of saying the same thing, but that is really, really important, okay? So a pure substance, okay, of a single chemical has its own chemical and physical properties, okay? So let me try to fix some of this handwriting. Still getting used to tablet writing. That's not any better. Okay, I'm just going to give up with that. So it has its own chemical and physical properties, but also it cannot, oh my goodness. By physical, okay, so let's read from the top. So a pure substance is a single chemical, all right, or one type of matter entirely made of one type of particle that has its own chemical and physical properties and that cannot be separated by physical means alone, okay? So in contrast then, a mixture is a sample of matter, all right, that consists of two or more substances, all right? So that's the differences here. Again, the water that we saw in our example and the salt water, okay? So here's a few examples here of pure substances and mixtures on both the macroscopic and the particulate level. Okay, so macroscopic level is on the top, particulate level is on the bottom here. So here we have pure bromine, pure water, all right, in these beakers sitting here. And then over here, we have small amounts of bromine and water, all right, and then a greater amount of bromine and water. And on the macroscopic level, we probably maybe couldn't tell exactly what's in the mixture. We would have to look further down in this example at the particulate level. So again, for the bromine here, there's just one type of particle, same with the water, but obviously in the mixture, both particles are present, okay? And what I mean to say before about we couldn't tell the macroscopic level is that the pure bromine sample looks a lot like the sample that has a lot of bromine and a little bit of water, okay? So one of the things to keep in mind then for these mixtures is that the properties of a mixture depend on the chemicals or substances in it. Okay, and that makes sense, right? Depending on what's in your mixture, it's going to have different properties and things like that. Okay, so here's another example of a mixture. So this is water and alcohol. So when you mix the two, they dissolve in each other. And these are images of that on the bottom here. And chemists consider homogeneous mixtures and solutions to be the same thing. And you might be saying, well, we didn't talk about homogeneous mixtures. Well, we will in a second. So here in these images, all right, this is pure water, okay? Right, this is pure ethanol or alcohol. And this is a mixture of water and ethanol, okay? So what do you notice about these things? I'll give you some time to think about it. All right, have you thought about it? Well, there's really no difference visually between these things. They're all in a graduated cylinder. They're all the same volume, it looks like here that they're taking out. They're all 50 milliliters by the look of it. They all the same color. So, okay, so what does that mean then? Well, if a sample is uniform in appearance and composition, okay, we define that as homogeneous, okay? So all of these samples would be examples of homogeneous mixtures. When I look at it, I don't see any variations in composition, appearance, so it's homogeneous. So the opposite then is true of something that's heterogeneous. It's not uniform in appearance and composition. So example would be if I mixed oil and water, okay? Where I'd have, you know, some, if this is my beaker here, I'd have some maybe oil. This is going to be a terrible drawing. Okay. I could tell already. Forgive me. Right. And this is, let's say, water. Right. So this is water. Oh, man. Come on. Come on. Come on. All right. Well, it's not letting me erase. You're going to have to trust that's an A. And this is, let's say, oil. Oh, it just erased. Okay. Awesome. Okay. So this is a heterogeneous mixture. Okay. Cereal and milk, right? There's the cereal floating in the milk. It's not uniform in composition and appearance. Okay. So this is a heterogeneous mixture. You could clearly see differences between the two. You can clearly see that there's things mixed up together in there. Okay, so here's an example problem. Why don't you pause the video and go through this example where you're classifying things as being either heterogeneous or homogeneous. Okay, so I'll let you pause the video And you can obviously unpause it when you're done with the example. Okay, so these aren't particularly hard, right? A small amount of salt dissolved in water. Well, you're not going to be able to really tell the difference before and after you put the salt in there. It's going to be uniform in composition and appearance once the salt is dissolved. So this is an example of something being homogeneous. Okay, a lava lamp, and put the picture here. It's this, I should say really the stuff inside the lava lamp is what I was referring to, but this is heterogeneous, okay? It is not uniform in composition and appearance. Pancake syrup, that is homogeneous, okay? It's uniform again in composition and appearance, and it tastes really good. So those are examples, all right? And those are the type of examples you'd have to do on a quiz or a test, all right? So keep that in mind. And now we're going to talk about one final thing for this video, and that's going to be the separation of mixtures, okay? So there's several different ways we could do this. And our goal is we just wanted to be able to describe how distillation and filtration rely on physical changes and properties to separate components of a mixture. And why this is important is that samples of pure substances are really rare in nature, okay? So chemists must be able to separate mixtures into their components, okay? It's common in chemistry. Depends on what type of chemist you are, but generally speaking, chemists must be able to do this. And most methods for separating things depend on differing physical properties in the materials, okay, among the components of the sample. So here's an example. So let's say we had iron with sulfur, okay, in the bottom here. It's mixed together and we wanted to separate the iron from the sulfur. Well, how would we do that? Well, we can rely on the physical property of the iron, magnetism, and that will allow us to separate these two components. So you put the magnet in your mixture, stir around, the iron filings get stuck to the magnet, and you could take them off the magnet and repeat the process to separate iron from sulfur, okay? So that's one example. So iron is attracted to the magnet, sulfur is not. Another example here is distillation, which I mentioned a little while ago. And this is going to separate things based on their boiling point, okay? Or it's just relying on boiling a mixture. So here we have a little flame, okay? Flame, Bunsen burner, okay? Where here, let's say in this example, let's say this is salt water. Oh my goodness, it's not bad. Okay, there we go. Okay, salt water. Sorry about this. Don't know why it keeps doing that. Okay, salt water. We'll just leave it at that. I don't think it's going to listen to me. That's salt water. All right, and what's going to happen? The flame is going to heat up the salt water. The water is going to begin to boil. Okay, it's going to evaporate, like we saw with physical changes in states of matter. So the water is going to make its way up the water molecules. Okay, there's a thermometer to register the temperature. And then it's going to go down this arm. Okay. And as the water molecules go down this arm, they cool down, okay? Because it's away from the flame. You can think about it that way. And so when they do, they're going to begin to condensate, and they're going to be here at the bottom of this flask, okay, as liquid water. And I didn't mean to erase water there. Sorry. I'm falling apart. Okay. And the salt isn't boiled, right? The salt isn't leaving with the water. So it's left behind in the distillation flask, and the water is at the bottom of another flask, okay? So that's an example of distillation. We separated the water from the salt. Finally, we can separate sediment through a filter. This would be the same idea of, you use a filter to keep coffee grinds from getting in your coffee when you're brewing it. Same idea. Okay, you have a filter, a funnel, and you pour a mixture of a solid and a liquid together, and you'll get the homogeneous liquid afterwards. Okay, so chemists rely on these techniques and many, many others to separate mixtures. Okay, so that's it for this video, talking about, like I said, separation of mixtures as well as compounds and mixtures. And in our next video, we're going to be talking about elements and compounds, I believe.